So we were in the middle of the proof of what we call the magic lemma. And I will repeat the statement of the lemma in a little bit, but first I will repeat what exactly we proved. So I'm reminding you that we have a set that we called C, which is a finite set of points. Right? And in the first part of the lemma, what we did was that we had some fixed k, bigger than 3, fixed. In the pictures, they were all, k was, I think, taken to be 4. And we had a hierarchical tiling of the plane, right? So G0 was 1 by 1 squares, right? Covering the whole plane in some way. G1 was k by k squares. And it was important that the tiling G1 is on top of G0, right? So if you have a k by k square, it's tiled exactly by 1 square. So this is on top of G0. And this way we defined, bigger and bigger squares, and also squares that become little, right? So there was a Gn for any n that is an integer. Right, and we called a square S belongs to Gn, right? Some square S supported, right? If the cardinality, the number of points inside that square, once we remove any of its subsquares, is at least S. Right, for any S prime belongs to Gn minus 1, and S prime is a subset of S. Right, if we don't require that this is a subset of S, I can erase that because it's even if it's not, then obviously you're not removing any points when you're taking S prime, right? And so the picture was this: we had some square. And we divided it, in this k, it is k equals 3, right? And we want to, and this is S supported, if I have S points here and S points here, right? This is one configuration, right? But perhaps I'm spreading it a little bit differently, right? Perhaps I have 9 squares, and if in each of them I put S over 2, right? This also works, right? Because 9 times S over 2 is bigger than S, and if I remove anything else, I remain with at least 8 times S over 2, right? Which is at least S. In fact, even S over 4 would work for this. So this was an S-supported square. And the statement that we proved using the hand-waving argument with the marbles, right? So we proved the number of S-supported squares, no matter what k is, cannot be more than twice the cardinality of C divided by S. So when S is large, you cannot have many such squares. If n is the total number of points, it has to decay with n. Okay? So this is what we proved. And what we want to prove is the following. So now I'm reminding you the statement of the magical lemma. Right? So we have for each W, right, a point, we have its radius of isolation, so we call that rho of W, which is the minimum of the Euclidean distance between V and W for all the points V in the point set except for W, right? So for V belonging to C minus W, and we said that the point, so now we have another parameter, right, delta. I mean, here we also had the parameter k that will, of course, we will choose it to depend on delta. So there are always these two parameters. Somehow delta tells you what the spatial size that you're looking around, and S is the parameter that we're saying how many points do we need to see inside. So this was the radius of isolation, and W belonging to a point W is delta S supported. Right? Let's write it first in a formula. If I look at a ball of radius delta to the minus 1 times its radius of isolation, so I take the radius of isolation, multiply it by delta to the minus 1, it has to have many points inside. But not only does it have many points inside, it has many points even if I remove any teeny-weeny other ball somewhere inside of radius delta times the radius of isolation, right? So it was written like this. So the infimum over P in R2, right, over any choice of center to remove a tiny little ball, right, of the number of points in C intersection with the Euclidean ball, right? So I'm writing it, I'm not sure that I wrote it, what was exactly my notation for a Euclidean ball, but now this lemma only has Euclidean balls. There's no graph structure, right? There's only points in the plane. So this is BW of radius delta minus 1 rho W. But I'm removing a small ball around P. And if no matter what is the P that I choose, the number of points that I see inside is bigger than S, then I call it delta S supported. B P delta rho W, close the cardinality sign, and this has to be bigger than S. Right, and the picture is, I have a point, so I have points in the plane spread out somehow, and of course I don't know anything about it. The whole point of this lemma is that it applies to any, no matter how I put my set of points, right? So I have some points here. Right, so my radius of isolation in this example is, right, if this is my point W, right, this is this is rho W, right, I'm looking at a much bigger circle, delta minus 1 rho W, and I need to see many points, right, many points of my set inside, at least S points, but as long as they're not all located in the same small ball, right? So if somehow I could remove a ball here of radius, this is the point P, and this radius is delta times rho W. This radius is, the outer radius is delta to the minus 1 rho W. If all my points are in here, right, then the point is not delta S supported. And if the points are somehow spread out, then the point W is delta S supported. And our goal was to show, right, so the theorem, the magical lemma, right, is that the number of delta S supported points, right, can be no more than some constant. Well, we'll figure out what this constant is. A constant that doesn't depend on anything. The number of points and divided by S, right? And here there will be some constant depending on delta, and it will be important for us for later, you know, so for right now we can think of delta as small but fixed and S to be very large. Later it will be important to me that's what's written here is a polynomial in delta. Okay, so we have any questions about the statement and what we proved so far? Okay, so what we have is a very similar statement, right? Something about squares, but we want to prove something about circles, right? So why, you know, what is the connection between the two of them? So let me tell you what the connection is. Right, so if we have, so the problem is, so when we have our squares, their scale in the beginning is 1 by 1 square, afterwards it's a k by k square, afterwards it's a k square by k square, right, and so forth. So if we have a square, right, let's say I have a square, and inside there's a point, and let's say I know about this point, that the point is somewhere in the middle of the square, right? And let's say exactly in the middle, or close to the middle, right? And its radius of isolation, right, is, let's say, you know, something of order half the size of the square, right? So it fits snugly in, right? But it doesn't reach the boundary so much, right? And so if I have, and this is the radius of this is not the radius of isolation. This is delta minus 1 rho w, and this is rho w. Delta is fixed, right? S is fixed. So if I manage to, and I have a point here, w, and this point is delta S supported, right? So that means that I can whatever point here that I remove a small ball, I see many points. I have many points of my set. So if the picture looks like this, right, then it's actually not that hard to verify that if this point is delta S supported, right, then the square has to be S supported, right? As long as, right, so here I have something of radius, right, here the big ball is of radius delta to the minus 1 rho w, and here the radius is delta rho w. Delta times rho w is the radius of the small circle, so we understand, so for this to work I also need k, right, k is the size, k is the how much I scale each of the squares. So for this, you know, so I want to claim so this is the kind of claim that I want to make, that I'm still not making. If w is delta S supported, then the square S is S supported. But I have to take, for this to work, as you can see, because this is of order delta to the minus 1, this is of size delta, I have to take k, which is k from this square. I have to take k, which is of order delta to the minus 2. Right? This makes sense, right? Because if I want to capture this small place with some small square, right, it has to grow from delta to the power rho minus 1 to delta to the minus 1. From delta to delta minus 1, that means it jumps by delta to the minus 2. So if the picture looks like this, I have a set of points, right, the pink points here in the plane in some arbitrary configuration that I know nothing about. And if by some magic or luck, perhaps magic would be the right choice of word, if somehow I manage to put the squares such that I capture all of the delta S supported points are just like fit nicely inside some square that fits exactly in, then everything works. But how do I know that I really managed to capture such all the points? Perhaps the square goes right in the middle, right? Or perhaps the squares are not in the right size, right? Perhaps they jump, you know, not from right. This has to go. I don't know in advance what is rho w, right? So perhaps rho w, you know, I don't even get. Perhaps in my construction, even if I choose k like this, I never manage to get a square that has size that is comparable to delta to the minus 1 times rho w, right? So it's possible, and you could draw yourself some pictures that it really is not something that you can hope for in any tiling of squares. So the point is to randomize our construction of squares and to hope that we capture not all of the delta S supported points, but at least most of them. Okay, so this will be what we will do. And this is the idea of how to reduce from this case, how to reduce to this case. Okay, so I'm going to erase the part about the square. And so the proof that I'm about to show to you now is starts at the middle of page 53, so you could follow as we go. So this is the proof of the magic lemma. Again, we choose k to be 20 times delta to the minus 2. It's supposed to be an integer. The 20 will only matter for our calculations. As long as it's of order delta to the minus 2, it should be clear. This will be the delta minus 2 in here. And the 2 really comes from the fact that we are in 2 dimensions. And I should also mention that this lemma, you can prove it, it holds in all dimensions. This is not just true for R2, but the same lemma holds in RD for whichever dimension. So this is not even special for a planar point set. And now we want to do something that in computer science they call it random padded partitions. So we want to choose the scale, right? So we're in our original construction of squares, we started from 1 by 1 squares. Right? So this means that our jumps will have to be from 1 to delta to the minus 2, right? And then delta to the minus 4. But there is log of 1 over delta scales between 1 and delta to the minus 2. Right? And I want to choose one of these scales at random, and that this will be the size of my original, of my first square tie. Instead of 1, right? So if I have, right, I have 1, 2, 4, up to delta to the minus 2, or sorry, or was it delta to, right? So I have here log of 1 over delta scales. Instead of starting from 1 by 1 squares, I'm going to start from a randomly chosen number from this point, some randomly chosen number, and this will be the size of my first squares. And then I'm going to divide everything by k, right? Or multiply everything by k, right? So this is what I am doing, right? And this will be important for me just so I could capture every, or at least some good fraction of these delta s points in a way that looks just like the drawing here. Okay, so I choose beta, which is a uniform random variable between 0 and log k, log on the basis of e, right? This is just a uniform random variable, and I look at say g0 is going to be e to the beta by e to the beta square tiling squares. Right, so this is e to the beta, a tiling of all the plane with squares with this side length. Right, this is a random side length, and this is g0, and then I continue from there. Right, defining g1, which are e to the beta times k, is the side length of each square. Squares tiling R2. So this will be the same thing. And in general, g to the n will be, this is not equal, this is just a symbol of what it is, e to the beta k to the n squares, side length of a square. And n again can be also a negative integer. But there is one more, so there's one more. So this is the first randomness in this construction, the choice of the initial side length of the square. But there's another choice that I'm making that is related to what you asked, Balint. And you remember when we started with 1 by 1 squares, right? So here is the tiling, right? And now I want to put 3 by 3 squares on top of this, right? So let's say this is 0 here. Let's say this is the origin. And I didn't even mention how am I doing this, right? So the one possibility is to put it like this. Just I take the origin, let's say I choose a point, and I put, the next square, the square on top, to be like this. But I've also started from this point, right? Right, and then tile it according when this is set. Now I have just a unique tiling by k squares. How many choices like this do I have? Right, so notice that if I had chosen this point to begin with, or this point to begin with, it's the same tiling. Right, so in total I have how many points can I choose in each step?
9.
Sorry?
9?
9, yes, or k square. Right, k square choices. Right, so now my extra level of randomness, I started with g0 somewhere, right? the initial point doesn't really matter. For complete, we could choose some random point, a uniform random point in some unit square. And now when I want to get to G1, I choose out of the k-square options of putting the tiling, the bigger tiling on top of the smaller tiling, I choose it uniformly at random. Right? And then from J1 to go to J2, I choose another uniform discrete, right, on a finite set, a random variable. Out of the k-squared choices of putting the tiling that is a little bigger, I choose that again, independently of everything. And I also do that in the reverse direction. Whenever I want to put smaller tilings, right, smaller squares, I also have the same choice of how to put them. Okay, so let's write it down in not many words because it's clear. So so for each what is the words that I used for each n? Well, for each n, we choose, and given Gn, we choose Gn plus 1, right? It needs to be squares that are bigger up to a factor of k. We choose it according to the k-squared possibilities uniformly at random. We choose the Gn plus 1 out of the k-square possibilities uniformly at random. Okay, so this is now our construction, right? So now we have we've made all these random choices. There's one here, one continuous choice here, and another countable many independent choices of k-square possibilities. And we want to say that with good probability, or that we see this picture for many of the delta S supported points. So let's define exactly what is this picture. So if this picture holds, we will say that W is a city in a square S. Right, so this will be this picture. So let's define what it is. So W, the definition, W is a city in S, if and only if. Two things have to hold. One is that the edge length of S is in the set, so it's either between 4 delta to the minus 1 row W and 5 delta to the 1 row W. The constant 4 and 5 were just chosen so that things will work. The thing that is important here, right, that this here I chose perhaps the constant to be 2, right, that the side length is of the same order as delta to the minus 1 row W. Right? If we know what the point is, W, then we know what row W, right? So this definition depends, you're given two inputs, W and the square S. So this is the first thing. And the second thing, as I said here, the center, right, the point W has to be close to the center of the square. Right? So the distance of W from center of the square, right, the center of mass of the square, right, just the middle of the square, is smaller than delta to the minus 1 row W. Okay? So now, the only thing that all of this randomness in the choice of square was used was for the following fact that we will observe, that if I have some point, the probability, if I'm taking some point W, right, the probability that it is a city has to be a good probability. And how good it is going to be? It's going to be good. Let's write down the statement. It's going to be, we want it to be a constant. It cannot be exactly a constant, at least with this construction. So the claim, given W and C, the probability that it is So notice, by the way, just by this definition, if it's a city for a given square, it can only be a city for one square, right? Because the other square, the other square, either if I move in the same scale, right? So I move to a square of the same size to my left, then this will be violated, right? The second thing. And if I look at a smaller or bigger square, then the first requirement will be violated, right? So there's just, if you're a city, there could just be one square, which is kind of obvious by this picture, right? So the probability that W is a city for some S is, we want it to be large because we want to reduce from the case of squares. So this will be at least some constant over log of 1 over delta. Right? And let's see why this is true. So the first requirement will be taken care of by the uniform choice of beta. Right? So the first requirement, first bullet. So we have to have a square that its side length is like this. Right? Without it, of course, nothing can. So there has to be a square for the first bullet, right? There has to be a square. Has to be a square with side length between 4 delta to the minus 1 rho W, right, and 5 delta to the minus 1 rho W. So the point is we don't know what rho W is, right? If we knew, for instance, that it was 1, right, then I could choose my initial scale to be something like 1. 1 would be good, right? Because then if I started from 1, the next one is going to be of size delta to the minus 1. I want it to be between 4 or 5, so perhaps I would need to choose, slightly bigger, right? But for this thing to hold, right, we need, right, that there exists some n, right, some integer n, right, so that e to the beta times k of the power n, e to the beta k of n, is in this interval, right? So let's do the calculation, right? And indeed, the reason is, of course, because these are the size of our squares. So we need, right, we take log on both sides. So we need beta plus n log k. And k, I'm reminding you, is delta. K was 20 times delta to the minus 1. So let's just write here delta to the minus 1. Let's just write log k, right? This needs to be in delta of of delta to the minus 1 rho W plus this interval log of 4 log of 5. Right? And I claim that, right, so what's going on here is that we have some fixed point, right, on the interval. This is some point. I don't know what it is. It's somewhere here. And now, and this is of order, right? This is of order log of delta to the minus 1. Log of log k is of order log of delta to the minus 1. Right? Beta, yes?
Define k to be 20 delta.
Yes. 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 This will not. Yes. This. Yes. This. Yes. That's what I defined it. So it's delta. So there's another 2 here. Right. And beta, right, goes and jumps. Beta is a uniform random variable between 0 and log also of delta to the minus 1, right? And we want to fall in this interval, right? So this is this interval. So I have a point here and plus some interval of a constant size, right? Some interval on the constant size, and I want to make sure that there is a point beta that I fall inside. So for any given beta, right? For any given beta, I'm adding to it intervals of length log of delta to the, sorry, I'm not adding, I'm adding, for any given beta, I'm looking at all of its translates, right, of distance delta to the minus 1. Right, so I'm looking at each beta here, 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 and so forth. Right? So perhaps I missed this. Perhaps for a particular choice of beta, I missed it. But it's clear that there's going to be an interval exactly of this length, so that if beta belongs to it, right, then all the values here fall exactly in here. Right? So in order for this to work, beta has to belong to some interval of constant length. Right? Something between log 4 and log 5. This is the length of the interval that beta needs to be in, but beta is a uniform random variable like here, right? So let's just write beta has to be inside some interval, right? This is an if and only if for this condition to hold, right? For this e to the beta k to the n to be inside here. So beta has to be inside some interval in 0 log of k of length, log 5 minus log 4, some constant, right? And this has probability at least constant over log of k, which is some constant over log of delta to the minus 1. Okay? So this is a tricky thing. This is confusing in my mind. But this just takes care of the first requirement, right? So we have some point w, and this is delta to the minus 1 of it. And what we wanted, so what we know, assuming beta was chosen, what we know is that this length is something between 4 or 5 times delta to the minus 1. Right, so this is something like 4, perhaps, delta to the minus 1 rho w. Right, this is the size of the big square, but how do we know, indeed, that it was chosen like this and not chosen like, somewhere that it cuts this pink circle right in the middle? Right, we need it to be right here. Right. So what is the reason for that? Let's just say that without writing, because. Right, so we had a bunch of, so remember that we had a bunch of much smaller squares before we chose at random the big square, right? We had, teeny weeny squares here. Not teeny weeny, but a lot of them, right? And they are, the scale, right, is exactly delta to the minus 2, right? So the edge length is delta to the minus 2. Sorry, delta squared times this thing. So these things are of order delta times rho w, right? And now I'm using the fact that I had a second random choice, right? Where is the second random choice? It was I erased it, right? So I have this tiling of the whole plane by many teeny weeny squares, and now I have to choose where to put the base. So imagine it's all in here. Yeah, here I've drew some of it, and you imagine that it's all over here. And now I have to choose where to put the big square. Right? I have many choices. Right? I could put it here, and that will be good. I could put it here. That will also be good. But if I put it here, that will be bad. Right? And in total, I have k square choices to make. So what will be the probability? Out of these k square, what will be the probability that I chose something good? Right? A point in which I'm basing my big square so that it will capture, right? So that the origin will be of distance at most delta to the minus 1 from the center of the big square. My claim is it will be at least some constant. Some small constant, but that does not depend on delta. And what is the reason? Perhaps the reason is a little bit misleading. The reason is that if I choose any point that is somewhere in this area, right, or any point somewhere in this area, right, or any point somewhere here, I'm good, right? But these areas are of order delta to the minus 1, rho w, right? This is, perhaps if this is 4, then this is delta to the minus 1, or perhaps half times delta to the minus 1, right? So already here I have order k square points to root my big square and to get this effect. So from this I get another constant, at least constant probability that this second thing hold. And this is exactly what I want, right? So, and these are two independent choices, and once two of them are hold, then we get the W satisfies exactly this picture, okay? And what is good about this picture, we already said. If we have this picture, then we know that if W is delta S supported, then then the square is S supported according to the previous definition, right? And this is just, this geometric picture that I drew to you, so you can. The proof is very easy of that, right? So we had the first claim is that we can. The first claim, the important claim is this one, that's saying that if we somehow randomize both the scales and the location of the squares, I could capture many of the points. Like I can create squares that have the same scale, and somehow that the circles corresponding to the points is just in the middle, or close enough to the middle. Right. So, and the second claim is, of course, this statement. Right. So, claim 2. If W is a city in S, so the picture looks like this, and W is delta S supported, then S, big S, the square, is S supported. And all the constants 4, 5, and 20 were chosen so that this will hold. Right? And the proof is essentially what I showed to you here. Right? If it's delta S supported, then it's also S supported, and you can think about it just geometrically, and it works out. Or you can read the proof. Right? It's a very easy proof. So how do we finish? So to finish the proof, right? So finishing the proof of the lemma, right? So we know that the number of S-supported squares cannot be too large, and we know that if W is a city, if W is delta S supported, right? So let's do this formally. Finishing up, right? It's almost the same case. So if we have many delta S supported points, the probability that each of them is captured inside a square is at least 1 over log, right? So the expected number of points that are delta S supported and are cities is going to be the number of delta S supported points times constant over log, right? And this number cannot be too large. So let's do this formally. So the number of pairs, the expected number of pairs W and S, such that W is a city in S, and W is delta S supported, is delta S supported. Just by the first claim, this one is at least, right, the constant divided by log of 1 over delta times the number of let's just call it number of delta S supported points. Right. So we want to, so the number of delta S supported points is no more than this log times this expected number of points. Right? So now let's upper bound this expectation deterministically. Right? I have number of pairs of W is a point, and S is a S supported, is a square that contains that point, and that is good. And W also have to be delta S supported. So I'm bounding this number by the, so this expectation, right, is bounded above by the number of S-supported squares. So this is S-supported squares. I'm counting the number of such S's, right, because I know that they have to be S-supported, right, because W is a city. So it could be no more than the number of S-supported squares times, now I have to calculate. For each S-supported square, how many W's could I have such that this pair is counted in this set? How many W's could I have? Okay, this could be a bit of a, this is a complicated proof, I admit, so it could be confusing. But because I have a point here that it has to have radius of isolation, something like rho W, all the points that are cities inside the square has to have approximately the same radius of isolation up to a multiplicative constant. So the area of each such point, right, is rho W square. The total area of the big square is delta to the minus 2 times rho square. So the total number of points that I could put here that have radius of isolation, at least this, is no more than delta to the minus 2. Right? So here I will write, so this is at most times delta to the minus 2. Right? And from the previous, and this completes our deduction, right? Because we already proved that the number of S-supported squares cannot be more than 2 times C divided by S. From here, we get another delta to the minus 2. Right? And this gives us what we want. Right? The number of delta S supported points cannot be more than some constant, the total number of points divided by S times delta to the minus 2 log of 1 over delta. And this concludes the proof of the magical lemma. Any questions about the proof? So you guys are very nice. You know, when I first saw this lemma, I didn't understand one small bit of it. So you're very kind not to heckle me about everything. I hope I did a better job than when I was shown this lemma. The proof just, you know, if you stare at it enough time, and I think it took me many months to finally, you know, to really understand it. And it's a very ingenious proof. That's why it's called the magic lemma. But be relaxed from now on. This is probably the hardest thing that I will prove to you in this class. So we have went through this, and now from now on we will, you know, all we need to know is the statement of this lemma and to derive all sorts of applications from it. Right. So our goal, as I'm reminding you, is to derive the statement that if you have a local limit of finite planar graphs or maps with bounded degree, then this limit is a recurrent graph. And so let's see first immediately how we use, now that the lemma, while the lemma is still fresh in our mind, let's see how we use it. What is the corollary? And this is at page 54 of your notes, the corollary 5.9 right at the bottom. Let's just state it before we'll forget what the lemma is all about. And this is exactly how we want to use the lemma. So after the statement, you will also be able to forget the magic lemma until you meet it again in a dark alley. All right, so the corollary is as follows, right? So G is a finite simple planar map. Right, and we'll only use this corollary. G is a finite simple planar map. P is a circle packing. So let's write rho is a random vertex. Right, so the lemma, the corollary has randomness in it, just because the magic lemma is a statement. The number of bad points cannot be too big, right? So that means when I choose a random point, the probability that it's a bad. When I choose a random point, the probability that it's bad is small. So rho is a randomly chosen uniform vertex of your graph. P is a circle packing of G so that rho corresponds to the unit disk of radius 1. Rho corresponds to the unit disk, the unit circle of radius 1. Then there exists some constant a such that for any number r, right, and any integer s bigger than 2, the probability, and here the probability is only after the random choice of the vertex, right? So the probability such that for any p, right, the probability that the number of points that I see. So if you remember, if I have a circle packing, I used the term VD, right? D is for some subset of R2 to denote all the vertices that their circles have center in that set. So here will be V B0R. And this is the Euclidean, the number of vertices that you see with the centers at distance r from the origin. Once I remove any other point, so the minus is here, BP1 over r, the probability that I see here, a set that contains more than s points, is going to be small. How small? It's just going to be a r square log of r divided by s. Right. So what is the picture? So imagine just for our considerations that G is a finite triangulation. Right? So if you are in a finite triangulation, that also means that the outer face is a triangle. So you have 3 big circles, right? And all the points inside, right, and all of the other points are circles that are drawn within here, right? So now I'm choosing some random circle inside. I have, imagine that I have many points, right? And I'm scaling it so that this is a circle of radius 1. So obviously, I will see around me many things, right? I will not choose one of these 3 with good probability. And what the statement says is that if indeed I normalize this way, and now my circle is of radius 1, and I look at a Euclidean ball of radius r, right, then the number of points, the probability that I see here, at least s points, right, no matter if I erase any other, so not only that the probability that I see here s points, no matter what small region I remove, right, this is going to be small. So I just have to apply the magical lemma to the set of centers, and this will be the proof. Okay, so this is for any S. Yes, question?
We should put the random root at the origin.
Sorry, I don't.
Here.
This is the probability.
Yeah. And we should put the. So the root is.
Root is z equals 1. The unit circle at the origin. I can always normalize my circle packing this way. Does that answer your question?
So rho is a uniform chosen vertex?
Yes, random vertex.
Okay.
Uniform.
And it is put on the origin? Or
Yes, rho corresponds to the unit circle. Right?
Okay.
At the center at the origin and radius 1.
Okay. So both translation and the scaling.
Yes, I take the circle packing and I scale it so that the root has radius 1. Right? I have to scale to get such a statement. Right? So let's just see what the proof is. Well, the proof is just choosing the parameters in the. So the proof apply the magic lemma with the set C as centers of the circles in P, right? And S is the same S as it is here, and S equals S, and delta equals 1 over R. And then I claim that now, if we just stare at the magic lemma and stare at that statement, and we see that they're exactly the same thing. right? I have here a bunch of points, right? If I have the circle, it's a finite circle packing, right? So I know if I plug in the magical lemma with these parameters, I get that the number of bad points, the number of delta S supported points with this delta and S cannot be more than n times delta to the minus. This is exactly delta to the minus square, right? Delta to the minus 2 times log of 1 over delta. Here I divided by S, right? And I had, so it's the number of points, because I'm choosing a uniform random vertex, the probability is the number of bad points divided by the total number of points, which is n. So this gives me exactly this upper bound. Right? So this is all it means. If I circle pack a big finite graph and I choose a random vertex, I cannot see too many vertices here once I remove everything, once I remove every little bit, everything. Of course I can see, perhaps I can see many points converging to one, but that are locally inside some small thing, but this doesn't count, right? Always think about the example of 3 circles and then 3 circles inside and going further and further. If I draw such a thing, right, I will see many points at one accumulation point, but I will not see many points in any ball of radius r. Okay, so this is the corollary. Any questions about it? And now we've already proved essentially recurrence, right? Because what does it mean? Imagine that, what does it mean? Let's write the exact formal statement of what we get. So it could be a little confusing, right? You may ask yourself, so this is the picture of the bad thing, right? So that means, what is the good thing that happens, right? Let's not focus on the negative, right? This event is the bad thing, right? What is the good thing that happens with high probability, right? The good thing is that, right, it's the exact logical complement, it's the exact logical negation of the event written inside this probability. So what would this event mean? The event means, let's write it in the positive way, the event means that there exists a point such that if I remove all the circles that are in this point, the number of other points that I see cannot be bigger than S. Right, so I see not many points. Okay, so now let's take one more step and also choose S. Right, what will be a good choice of S? And this will be, and let's put it all in the following theorem, and I'll call it theorem 1 because I will want to use it tomorrow to prove something about the UIPT. So this will be the all that we worked so far. So U rho is a local limit of finite planar maps or graphs, whatever you want. Then almost surely there exists a sequence of sets BK. There exists BK that are a sequence is subsets of the vertices, subsets of U or V of U, such that 1, BK is of linear size, and 2, the resistance between rho and the outside of BK is at least linear in K. And let's not even think about BK is going to be chosen like this. If I have some good event, this is rho, and here I have not too many circles unless I remove this. So BK is going to be exactly, all the vertices that we see here. Right? And then if we remove it, ignore this little technicality here. If we remove it, we know as long as this radius is something like K, right, or some power of K, then we know from our previous resistance estimate that the resistance is going to be at least logarithmic in K. Right? So let's make this, let's look at the proof of this theorem. So the proof of this theorem is just this corollary with the correct choice of S, and then applying some Borel-Cantelli. So there's nothing really new in this, but let's do this properly. Now I can erase this. Oh, by the way, what does this, if we prove this, what does this mean? And in particular? So it's recurrent, right? So if we prove this, in particular, U is recurrent. So in particular, U is almost surely recurrent. We also have it in some quantitative way, which will be useful for us. Later. So what is the proof? Proof. So now let G is finite. Again, finite, simple, planar map. It's, and I imagine this G converging. This is a sequence of G's converging to U. But now I'm just looking at one of them. G is infinite and finite. And now I'm going to claim that then, finite and degree bounded by D, no more than D. And my claim is that the probability, right, I have a fixed graph, right? And again, rho is a finite vertex. Finite. Rho is a uniform random vertex. Uniform vertex. Exactly in the setting of the corollary. Then the probability that there exists some set of vertices. Then for all k, the probability that we have a set of vertices, b is smaller than k, and such that the resistance from rho to the outside of b, think about b as some connected set containing the origin. The probability that we have such a set, such that this is bigger than some constant log of k, right? So this is now the good event. So we want this, right? So this is, I'm choosing a random point, and the probability that from the vicinity of this point I can chop a little set B that is not too large, right? That it's at least linear in k, such that the resistance between rho and the outside is large, right? This is exactly at least 1 minus something that should be small. What is what we get? We get k to the minus 1/3 log of k. So the only reason that we get all these minus third log of k is just because we're going to choose R and S now in the corollary, yes?
You have to add the next degree into the theorem.
Yes, thank you. So here, a bounded degree. Right, I cannot hope to this, for this theorem to hold without the bounded degree. Right? We saw an example. Right? It was a canopy tree with some weights on it. We saw an example. In fact, a variant of this example is a solution to your exercise number 3 that is that I posted outside that you can pick up. So indeed, if you don't have a bound of the degree, you can get a transient limit. But the statement, but the fact that even if you have unbounded degree, right, the magical lemma, there was no graph structure, so the degree didn't mind. The statement that what you get is something that is packed all over the plane, right, what we call CP parabolic, is true even when the degree is unbounded. Right? But because we want to conclude something about the effective resistance, then for that we need the bound on the degree. Okay, so in fact, there is a statement here that could be stated for unbounded degree graphs. And for this, so let's prove this by drawing a picture. And I'm just looking at the corollary. Okay, so we stare at the corollary. Let's choose R and S, right? And then draw a picture, and which will be exactly the same picture. Okay, so the only thing here is to choose, right? So sorry for this. So now I'm continuing the proof, but I didn't want to erase the corollary. So we're all adults. This is not a part of the, right? So I'm continuing the proof. We choose R, we which is equal to k to the 1/3, and s equals k. Right, let's plug into the corollary. R square is k to the 2/3. S is k, so I get exactly k to the 1/3. So here is another log of k. So with probability, so by the corollary, the probability, with probability at least, what we want, right? 1 minus, I'll drop the constant, k to the minus 1/3 log k. Right? The picture looks like this. We have exactly the statement. V of b 0 k to the 1/3. Right? This is R. Right? So the statement is that there exists some point, right? The logical negation of the event in here. There exists some point in R2, right? Such that the cardinality, if I look at a ball of radius k to the 1/3 around my origin, once I remove this ball of radius 1 over r is k to the 1/3, then I see no more than k points. So what will be, right? So this is an application of the corollary. And what I want to prove is that there exists a b with at most k points such that something happens. So obviously, I'm going to choose b to be this set. Right? B, which depends on k. Right? So I choose this set to be b. Right? So what is the picture? So firstly, it's a linear size set. Right? So at least the first requirement is that right? The first requirement holds, right, with the correct probability. And so what is the picture again? Right? I have my root at the origin, and it has radius 1. Right? And then I have radius, which I chose it to be k to the 1/3. Inside, I have a drawing of many other circles. Right? And I know that the number of circles in here is at most k if only I remove something teeny weeny here. So here I could have exponentially, perhaps an exponential number of points. Here I can have a whole chunk of points. So if I remove this part, right, and this radius, right, the size of this part is k to the -3rd. Right, and here I have more and more circles drawn. I guess I'm assuming that I'm in the situation of a triangulation. And now I claim that the resistance and B is all the purple circles, so not including the circles here. And now I'm looking at the complement of B. So the complement of B is everything that is here, right, outside, but also inside here. And I want to claim that the resistance to the outside of this set is large. So perhaps the only thing that is confusing at this point that a lot of, I asked this myself, it's like many people ask this when they see this part of the proof, why are there even circles here? Right? Why does the drawing continue going up to here? What is the answer to that? Sorry? So you could argue, but what is a better answer if you're lazy?
We don't care because we want to...
It's even better if there are no circles here, right? Because we can always, if there are no circles, perhaps for some weird reason the drawing ends here. Just imagine that you add some circles here, right? You've added edges, right, or vertices, right? And the effective resistance can only drop when you do that, right? And even after you add these things, you still have a lower bound on this resistance, so you're even in a better situation, right? So in fact, the picture that we imagine that we have a lot of circles here is the worst case scenario, right? So that's why we do it. And the reason why there is indeed going to be many circles here is that we always think about the number of vertices in our graph, right? N, right? This number is very large, and all of these k's and r's and s, these are fixed numbers, right? These are fixed. So now I'm looking at some bounded radius, and I have a radius which is 1,000, but I have 1 billion vertices, right? So just by the ring lemma, they cannot all be concentrated here. They have to go outside. Okay, no, not just the ring lemma, but also the fact that you cannot see, except for this point, you cannot see too many circles, right? So they have to go outside, right? If they would like converge, you would see too many of them. But the honest truth is that we also don't care about this, right? So now all we have to argue, let's do that with a hand wave, is that the resistance from the middle orange circle to whatever is drawn in blue, so outside of the big orange circle, but also inside here, is at least logarithmic in k. So if this did not exist, right? If we would just look at the resistance from here to here, right? Then it would be log k just by what we proved, right? Just by putting annuli, right? And because we need to reach distance which is a power of k, we need logarithmically many annuli. Each annuli has resistance at least a constant, and we're allowed to add them by the series law, right? But now we have this little fucker. How do we deal with that? Could you please erase that from the? I guess. So what is the solution? Any ideas? An inversion. So what you're saying is, okay, so what you're suggesting, remind me your name? Mikael is suggesting, okay, so I can invert, but that means that what I have inside will be, I'm not interested in what's in the structure of the circles inside here, right? But what you are saying that is correct is that if I look at the resistance from the middle orange circle to all the cluster of the little points, the teeny weeny points inside, imagine that you have exponentially number of points here. This could indeed happen, right? You can have something like this. So the resistance between this cluster to the origin has to be at least logarithmic in k also. Why is that? Because the radius, right, the diameter of this thing is of order k to the minus third. It has to be at least of distance 1, or at least some constant distance from the middle circle, right? Because it's surrounded by circles of constant radii. That means that I could put here, again, logarithmically many annuli, and conclude that the resistance from here to all of this is at least log of k. So in particular to this is at least log of k, right? By the same kind of arguments of putting annuli and using the Dirichlet principle to get a lower bound on the resistance. So what we got is that the middle orange circle of radius 1 has resistance at least log k to the outside, and also at least log k to the small, little, very nice, and no derogatory term for this cluster of circles. And now we want to conclude that the resistance to their union is at least log of k. Right, so now I have a situation that is completely electric network, completely abstract. I have a network A and 2 points Z1 and Z2, right? And this is it's a strange network. I don't know anything about it. And I know that the resistance from A to the first sink is at least log, of at least some large number, and from A to the second sink is at least large. Why is the resistance from here to both of them is also at least log, perhaps with some other constant? That sounds very reasonable, right? What is the argument? Yes?
Parallel laws greater than half their minimum?
Where is the parallel? Right? You're using all the edges. Parallel law, you have to have a network like this, right? That is completely disjoint from a network like this. Any other ideas? Yes?
In terms of return time.
Return time. Okay, so let me translate from French. Right? What does it mean that the resistance from A to Z1 is logarithmic? Right? A log of k or some large number. It means that if I start a random walk in A has some bounded degree or some fixed degree. Perhaps the degree is 3. Right? Much smaller than log of k. So this means that if I start a random walk from A, the probability that I hit Z1 before I return to A is a constant over log k. And the same thing from here. The probability that I start at A and visit Z2 before returning to A is a constant over log k. So by the union bound, the probability that I start from A and I visit either Z1 or Z2 before returning to A is the sum of, at most, the sum of these two probabilities. So it's another constant over log k, right? And so you get, again, from that the resistance, right, is of order log k from A to Z1, from A to the union of Z1 to Z2. Right? So always thinking about resistances, sometimes in terms of current and sometimes in terms of probabilities of the random walk is very useful, as you can see in this situation. All right, so we proved this statement, right? And now we haven't, right? But the theorem that was written there said something. Firstly, that was almost sure, right? And secondly, what did it say? It said almost sure. So we need to make this occur for all k's simultaneously, right? But you can observe from this statement that if I know this event, right, not for all k, but for all k's which are a power of 2. Right? Then if I change the constants a little bit, right, I get exactly, I get that this event holds perhaps with different constants, but for all k's simultaneously. Right? So the fact that here this is k to the minus third, it means that I could replace k by 2 to the power L, right? And then use Borel-Cantelli on this event, right? Because the probability that the event doesn't occur is exponential, right? Is 2 to the minus L over 3. It's exponential in L, so it's summable. So you only have finitely many of these events that do not occur, right? So all of them will occur simultaneously, and you get the recurrence. Are there any questions about this proof? Okay, so perhaps it's a little bit, it's a lot to grasp. Yes, is there a question?
Where we use the local limit?
Because we choose a uniform random vertex, right? So this is a good question, right? The statement of the theorem was you are given some local limit rho u. How do we obtain such a local limit? We have a sequence of finite graphs Gn, and for each of them we choose, right, rho n, right, a random vertex, and we want to say that, and we look at some fixed k. We look at this event, right? So what we learn is that, so we look at this event in the finite graph. This is an event that can be, if I'm given some k, this event can be determined locally from the graph, just by looking at some radius, graph distance radius of some function of k, I can determine this. So if this is true for each fixed finite graphs, it is also true in the limit. Right? So in fact, I get this statement before I'm using Borel-Cantelli, I'm getting this statement for u rho. Right? And it's exactly the same statement. The probability that there exists some set B of linear size, such that the resistance is large, is at least this on the infinite graph, right? Not just on the finite graph. Right? Because for each n, I have here a limit of some event that is locally determined, right? And that is it. So I get this for the limit, and I apply Borel-Cantelli on the limiting graph, on u rho. So thank you, it was a good comment. Okay? Any other questions about this proof? Okay, so this I know that this was hard, so let's try to continue with something a little lightweight. So this tells you that so notice that Right? The statement of the theorem was you have a set that grows linearly that has the resistance to the outside of it is logarithmically, right? And you have such sets for all k. That is almost surely there exists a sequence of sets that grow linearly, and their resistance to the outside of them is logarithmic. This in particular implies recurrence, but of course it's a much stronger statement, right? It tells you have small sets, that you have logarithmic resistance to the outside. And if I just want to prove recurrence, I can actually argue a little bit easier if you don't like this whole thing. The reason that I chose to do this whole thing is that we're going to use this quantitative version for the next step to prove that random planar maps where you don't have the bounded degree are also recurrent. But what you get from this picture, right, or what you get from using the corollary, right, and getting this conclusion, right, and ignoring the effective resistance statement here and using again the Sem-Borel-Cantelli, what you will get is that any local limit of planar graphs, even if the degree is unbounded, if you look at the circle packing of it, right, it will be a circle packing such that the carrier is all of the plane, perhaps minus a point. Right, and this is the truth, and unfortunately, this could, if there's unbounded degree, you could still be transient. Right? So if you do have bounded degree, then we've already argued that just from looking at if the carrier is all of R2, then we know that we are recurrent, and if it's minus a point or minus 3 points or any isolated set of points, then we can invert around that point, get recurrent graphs around the inversion, and we paste them all together, and everything remains recurrent. So I could have chosen a slightly easier way to proceed, but I wanted the stronger version. If you are even more lazy than that, and you want to see a proof of this theorem that doesn't even require the magical lemma because you didn't like it, then I recommend you can open the what will I erase? Let's erase the corollary. You can look at, so recently we have obtained a proof of this, of the statement that any local limit of finite planar maps is recurrent without using the magical lemma. So look at the paper, unimodular, don't be afraid of that word. It just means local limits, but it's a cooler word that allows you to steal money from the government. Unimodular, random, I'm not sure if the word random is there, triangulations. They're circle packing and random walk. And this is by Omer Angel, Tom Hutchcroft, yours truly, and Gurab Ray. And there you will see a proof that doesn't use all this machinery. However, it has two caveats. One is it doesn't give you this quantitative bound. It just gives you recurrence. In fact, it only gives you that the limit has to be parabolic in the sense. So no quantitative version. So you cannot proceed from that proof to prove that, at least to our knowledge, to prove that the UIPT is recurrent. And secondly, it uses other machinery that you perhaps won't know how to prove. One is you'll have to know what is hyperbolic geometry just to see the proof. And also you have to know the statement of Schramm's rigidity theorem that I told you, that if you have a graph that is transient, the proof goes by contradiction. So you assume perhaps that the circle packing that you get is a hyperbolic, and you aim to reach a contradiction, and you need to claim if it is hyperbolic and be packed in, then it can be packed inside the unit disk, and this packing is unique up to Möbius transformations of the disk. And if you assume or know these two things, then the proof is pretty soft and gentle, and you get it for free. So if you're interested, then I recommend it. Any other further questions about local limits of finite maps with bounded degrees?
Yeah, just about this proof in question. Okay.
You just read it. That was 2-3 seconds it took you. I'm impressed. Yes, sorry. Did I confuse you?
Yeah, if you want to prove that the map is recurrent, you don't need the linear, the logarithmic growth of the resistance. Right?
That's true.
Okay. Is there some kind of result about the sharpness of the growth? Is it really logarithmic?
Yes. You're asking, can it be more than logarithmic? So who knows of a planar, infinite planar map in which the resistance to the ball of radius r is not just at least logarithmic, but also at most logarithmic? And let me give you a hint. It doesn't matter if it's the graph distance or if it's the Euclidean distance. Sorry? The regular grid, right? The regular grid, Z2, right? If you look at the ball of radius r and Euclidean or graph distance, the resistance is not only not only logarithmic at most, but also at least, or not only at least, but at most. By the way, how do you prove that? Okay, so the lower bound we know because if it's at least the, assume that it's the triangular lattice, it's the same thing. The lower bound we know, we put annuli, we have on each point at least, at each annuli we have at least a constant. How do you prove, just for Z2 or for the triangular lattice, that in a ball of radius r, the resistance, right, from the origin to the outside is at most log of r? Oh, with cut sets it's much easier, right? You have a cut set right here, right, and here. So this is a cut set of radius 1, this is of radius 2, and the cut set of radius k has k edges. So it is 1 over k, right, at each cut set, and you get, oh, sorry, this is a lower bound. You lied to me, right? Yes, Sebastian? A random path is a good way to do. So I leave you, this is an easy calculation that you could do while smoking half a cigarette. After now is you choose a random point here and take this discrete path going to here and calculate the energy of this path, and you will see that on each annulus the energy that you get is at most a constant. You add all these energies, you get log. The energy that is wasted in this random path is log of k, and this gives you an upper bound on the resistance. Okay, so does that answer your question? Any other questions? Okay, good. Then tomorrow we will prove that a random planar map, the UIPT, is almost surely recurrent. And I'm reminding you, let me just, before I finish, the statement. Just write to you what the statement is, so we won't have to repeat it tomorrow. The statement is, right, so theorem, right, U rho is a local limit of let's just say planar, a finite planar maps such that instead of having bounded degree almost surely, you know something about the distribution of the degree of the root such that the probability that the degree of the root is bigger than k decays exponentially in k. Right? So this is, a legit assumption, right? You have the degree of rho is indeed a random variable that you can look just by looking at the neighbors of rho. You can determine what is its size. Then U is almost surely recurrent. And I'm telling you as a fact that the UIPT and the UIPQ and most models that we know of a random planar map satisfy this condition. It's not even very difficult to see, but I don't want to, in this course, we will not construct a random planar map and verify that it has this thing. We'll just prove it using the tools that we developed so far, using the theorem that we have seen. Okay, so we'll do this tomorrow. Thank you. Thank you very much.